Now, when we looked at the video, you saw a very good representation of the operation on surface, and I like the narration of that. It's very good. I'm going to quickly go through a similar description of what we're doing on the surface with all of that equipment. And here we're starting off with the tanks that are holding the fracturing fluid. In some cases, these fracturing fluids are pre-blended and pumped in there. In some cases, they're blended on the fly to get some chemicals in, or additives we call them, into those fluids before they go to the blender. In the great majority of cases, there's not much of that pre-blending. It's a lot of cases it's where we're just using regular plain water. And one of the things I want to mention is that in fracturing in other formations besides shale, there are other types of fluids that we use besides water-based type fracturing fluids. One of the common ones are foam fracturing fluids, which significantly reduce the amount of water that you can use. And when I worked in Ohio, West Virginia back in the early 80s, we did a lot of foam fracturing in those areas for the Devonian shale gas production. They didn't have very many horizontal wells back there that I could recall. So the idea of doing a bunch of fractures in horizontal wells really was just a dream back then. And it was somewhat later that we realized that that could really work very well in the other shale zones. But the Devonian shale in those areas are quite water sensitive. So we were trying to actually reduce the water exposure to those formations while we're doing the fracturing operation. But in a lot of cases, it takes a lot of fracturing fluid to get the large number or amount of proppant down into the cracks in those formations. So we're going here through a pump that pumps it into the blender. This is a representation of the fluid that's stirring around in here, and sand is being augered up into this blender so that while we are pumping the fracturing fluid, we're actually adding the sand to it before it hits the pumps and goes down hole, which is further along the line here where we get into the high pressure pumps and then on to the wellhead. Now, all through this process, we're doing a lot of measurements that we'll see a little bit later that we can control. The amount of proppant, we can control the rates that we're flowing at, and a lot of other things, including the density that we can check to make sure all the materials are going into this mix in the proper proportion. So here, let's explain a little bit more about why hydraulic fracturing works in horizontal wells. Well, we have here a representation of radial flow with a hydrocarbon molecule, which could be either gas or oil, down there in that reservoir. And so we've got to get that molecule into the pipe, and it's got to go through rock to do that. So in the case of a shale, this rock is relatively difficult to flow through. It would take, in some cases, years or much longer to get that to just flow naturally in a lot of cases. So that's why we apply the fracturing. So if you had a lot of these molecules that were all trying to get into that pipe, it's kind of like a traffic jam where, you know, you're trying to get to the city center and you've got all of these streets going into the center of that town at the peak traffic hours, so they're going to run into each other. And when they do that, obviously they slow down and you have traffic jams. So it makes it very difficult for an unaltered rock to flow into that pipe. So let's look at the solution, and that we call that a linear flow solution as opposed to a radial flow. We've got the same hydrocarbon molecule down there trying to find its way into that well, and we're applying the fracturing operation. And that means that instead of going this distance, it only has to go from here to the fracture in order to come through a relatively easy pathway to the well. And all the other molecules can have a similar, let's say much less congested pathway from where they're sitting in the rock to that fracture, so they can all produce faster. Now, one of the things that we really like to focus on in well construction and well integrity is to isolate the groundwater. And that is typically a few hundred feet below the surface. And there's a lot of state regulations that we've been following for decades to keep that water protected. In other words, make sure that we have good pipe and good cement that will block the flow of hydrocarbons into those zones. Now, one of the things that we also have to look at is what is the potential for leakage from the reservoir into those formations. If we do a good job here in isolating the formations, in other words, keeping that hydrocarbon molecule down here and wanting to go into the well here as opposed to coming up along the side of the well and getting into the wrong place, we have a lot of rock here, and in almost all cases we select these reservoirs because they have naturally occurring rock that's just about impermeable to any flow. Now, if you're willing to wait around a few million years, you can get some hydrocarbon molecules up this rock. But hopefully we're going to deplete the oil and gas out of those reservoirs here so that those molecules won't have any chance to get through that rock in a million years. So that provides what we call zone isolation of the reservoir itself. A lot of state regulations that deal with that to make sure you've selected a reservoir that has the right characteristics to contain the hydrocarbons. So when we design for the fracturing operation, we're designing where we're putting the perforations and how big these fractures need to be in order to get the right production. We also make sure that the fractures will not penetrate those formations that are actually the low permeability formations that are containing the hydrocarbons in that rock. And we do a lot of complicated calculations. Just about all of them have to be done on a computer. I used to do them by hand years ago when I started. For example, that job in 1974, I actually had to go through these things here, you know, and it took me, I had to stay up a day, do that, and I worked it in the night, you know, many hours. Well, we can do this on a computer in seconds now, so it's not a big problem. But believe me, when you look at the first what you might call trial calculation, that's just one scenario that might happen, and it may not be the best one. And what we have now are computer software that can repeat it without me having to press any buttons and give me a whole variety of conditions and scenarios where at the end of the minutes, or in some cases an hour when it's really complex, the computer can show me up to 100 iterations of all of the different things I might could do on this fracturing design, and then I can go back and I can pick out the best one for production, that also has the criteria to not have a fracture too big. And that also, those computer programs also give us what we call the pumping schedule. It'll tell us when to pump different materials and in what time period to pump them, and help us understand that if we pump a certain amount of sand that's too high in the early parts of the operation, I may not have a good placement of the sand in the proppant. So I need to space out that placement of the sand, and that means that I have to have the mixing operation on surface where I'm actually mixing and pumping it follow that same guideline. So it's not an easy job to do these things, but thank goodness we do have very good computers now that can help everyone understand what's going on. And we know that the computer software is just not untested, and it's a shot in the dark, because we've got a lot of data that tells us that the proppant went into the right place, and that the fracture was created in the right place, in right dimensions, and we'll show you a little bit of that later. This is some of the design information we need in order to design the fracturing operation. And there's a lot of data here, and a lot of what I tell the wireline loggers, squiggly lines, you know, different colors, that will tell us different things about that rock and that reservoir, the pressures and the types of fluids in place. And all of that data, or let's say the key parts of that data, are analyzed by the computer program to help us predict the right size fracture. And it will also help us understand what types of properties we have to have in the fluids. In other words, there's a whole variety of properties that we can have in fluids that will influence the size of the fracture in the formation. So, for example, permeability, is going to be damaged if we have the wrong fluid. So we optimize that to get the right materials to not damage the permeability, and to keep as much good permeability as we can. The same thing with the creation of the crack. Viscosity of the fluid is a big factor there, so we'll have all that type of information into the software to help us design it, including after the proppant is in place and the rock wants to close onto that proppant. We'll use data here that will help us understand, are we going to have enough permeability left through that pathway in the fracture with the proppant in it to get the production that we need. Okay, as we mentioned, fluids can be a whole variety of things. Most of them in shale wells, fracturing, have some types of polymers, and in a lot of cases those polymers are what we call cross-linked. In other words, they're joined together, kind of like, well, not like Jell-O, but that's what happens when you make Jell-O. You know, you have some things that kind of go together to give it some rigidity. We don't need that type of rigidity. We want something less than that that can still flow. And we have these chemistries for that will have to have a certain amount of pH control. In other words, it cannot be too acidic or basic in order for these cross-linking operations to succeed. Then after the fluid is in place and has put the proppant in the fracture, we have to have what we call gel breakers, because we've designed a certain amount of viscosity to get that proppant into the crack, and that viscosity has to go away so that we can produce through that proppant. So we design materials that will give us a break in that viscosity enough so that we can flow the well. In some cases we need surfactants to help that flow. In some cases the rock itself is sensitive to water, and we'll put in some materials that will protect that shale, for example, that's sensitive from being damaged. Otherwise, you could have that shale be damaged. In other words, it might swell a little bit, and we don't want to damage the rock. Biocides, we'll see here in some of the slides we have to show you some future, or some actually new things that we're doing, are meant to get the bacteria under control and prevent bacteria from having an issue with production. There are also conductivity enhancers that will help us maximize the permeability of the proppant pack that we put in the fracture. Fluid loss additives, so that we're not going to have some of the cracks take too much of the frac fluid, because if they do that, it's actually robbing the places that we want to put the fracturing materials. And then, of course, the proppants themselves. And there's a variety of different proppants. Sand, very special sand, is the most common one that we use. So, as we go through this process, let me kind of speed it up a little bit here. We've done all the things that we've mentioned in earlier slides, but we have people on the location in what we call frac vans that are monitoring this operation and checking all the data. And this is what a typical screen data would look like. It's telling us all the proppant amounts going in and the pressures, etc. And based on the shape and direction of those curves, we can optimize the fracturing operation to make sure we have a good, successful placement of the proppant. So we track the volumes that are pumped. We make sure we don't over displace it, because if you do, the fracture will just close in on that unpropped fracture and shut off production. We have to have that viscosity break. We have to recover those fluids from the fracture and dispose of them properly, which some of the other speakers will talk about that. And then production test the well. So here's a typical frac operation. We have all the storage tanks here for the fluids, the pumping units, the blenders, and the controlling vans where they have the people inside looking at all the measurements. And the data is collected, like I said, and monitored. We have a lot of things that we can do with that data to make sure that everything that we designed to do is actually happening. And one of the things that has been the best evidence that we're not fracturing into the groundwater is that in most areas we are doing what we call microseismic measurement during the operation. And these curves here represents where the fracture is down in the well. And then you can see there's thousands of feet of distance between the fracture and the groundwater. And this one is Ohio, Pennsylvania, a whole series of operations that were 350 individual operations. This is Barnett with over 2,000. And this one is the Woodford with over 300. In all cases, very good containment of those fractures. Now, some of the new things I'd just like to briefly mention is that we're looking at how can we get rid of some of these chemicals that we're using in the fracturing operation. And one of them that we've looked at in particular is the biocide. We can put these types of devices, which are bug killers, I call them, into the flow path of these fracture fluids and not have to use biocides. We have polymer systems that are very clean. You can actually drink some of these because they're using polymers and additives that are food grade materials, and so it won't kill you. And we are having here, that's the little ultraviolet bug killers, I call them. And then there are processes that we use to actually clean up the fluids that are relatively new. And one of the ones that is also very beneficial is where we're saving a lot of the fluids that we'd use for liquid additives by simply mixing dry polymers instead of liquid polymers into the fracturing fluid. And of course, we're still doing a lot of microseismic fracture mapping and making sure that we're having good success with isolating the well against the groundwater. And then we're also starting to report the chemistry of these fluids with particular processes that follow the state regulations. And this is just an ending slide to show you that we really need this production, because here we are in this time period, and in order to keep up the amount of consumption for energy for oil and gas, we need this gas shale to fill in about 45% several years down the road. Otherwise, we'll be paying more money than we want to for energy. Thank you very much. Any questions?